Okay, guys, we're live again. I restarted the stream. Do they need a link?
Uh, Sorry, I'm not even unmuted. Yes, I will send a link once I find it. Live? Okay.
Oh, the focus is nice. Likely due to. I might not even join Zoom just to conserve bandwidth.
You can even join from my laptop.
Yeah, let's
Okay, sure.
welcome there.
Good. Audio's good.
I'll do it here. Good morning, everybody. I hope we're live. Sorry again for the delay. Um, Having trouble with Xfinity again. And it's getting pretty typical. We've been immune a little bit to the internet slowdowns because we start so early. Um, but in the middle of the day, it gets really slow as people come on and start working. It's just traffic on the internet. Everyone in the world is in a Zoom by 10:30, and things slow down. So, but let's go. I hope the stream is reasonable and there's not too much delay, and you have a reasonable picture here. It'll help if you set your YouTube resolution down to the lowest that you need to read the screen. So don't run it at 1080 pi. Uh, if you can read the screen at 480, uh, um, you'll have better performance on your home internet. Won't affect what's coming to you, but it might speed up the the connection along your home Wi-Fi or your home wire. Well, we run around so much, I forgot what we're even going to do today. Um, I guess it must be polyprotic acids and indicators. Forgive me for fumbling around, but yes, we ended last time discussing polyprotic acids, and we found that polyprotic acids, we treat them exactly the same as our uh, monoprotic acids. We include another another equivalence point. So one proton titrates, one proton is removed, and that sorry, that corresponds to an equivalence point, half equivalence point here, where the pH equals the pKa, and then a second proton equilibrium, a second acid-base equilibrium. In this case, the acid and the base form are at equal concentration at pH 8.8 at the second pKa. So let's review that. Oh, come on. Is the board going to give me grief? Okay. We even got some sluggishness in the board this morning. Um, so many indicators, acid-base indicators, they change color based on the protonation state. And that's really handy because now we know the protonation state is a function of the pH. So this thymol blue is a indicator, and it will change from red to yellow at around pH 2. Protonated form is red. Then the first deprotonated form, the first weak base, is yellow. And there'll be an equal mixture of those at pH 2. And so the the solution will go from red, which is very acidic, above 2, it starts to turn orange and then yellow. And then the second weak base, after you've taken 2 protons off, is blue. So when you're up in the basic region, it's blue. Very handy. So you know immediately if you have a strongly basic solution or a strongly acidic solution, simply by the color of the indicator you put in. And we understand now well about these two pKa's where you're buffering. So it stays blue. It acts as a buffer around 8.8. That's handy. It's not dramatically changing color and stays reddish at low pH. So acting as a buffer and an indicator and a diprotic acid to give us several options. So a lot of the chem quizzes from here today and tomorrow are going to be chem quizzes that encompass a lot more. So we're going to go back in time and do a callback, as they say in theater, callback to something you've did earlier. So we're going to do a callback here to our spectroscopy and molecular orbitals. We're going to relate that to our acid-base chemistry in a relatively straightforward way. Thymol blue, we've seen, has 3 forms, the red, yellow, and blue form. Which of the pi to pi star transitions, I've shown 3 here, for the 3 forms of thymol blue has the greatest absorbance at pH 10? So when you get to pH 10 and you have the 3 absorbances that thymol blue has at various pHs, which of these thymol blue pi to pi star transitions correspond to the blue color, correspond to pH 10? Almost given 2. I'll show you the group of 4 here so you can think about that. Oh, we need to start a quiz. iClicker wasn't even working, of course, because that takes the cloud. So if you can start quizzes started. Ryan is remote today. And Ryan, who's an RA, there was a chance you would meet Ryan if you came to live in the residence halls. She's a resident assistant and getting ready to meet her incoming freshman. So she's doing trainings and moving into her room. So I think we have the chem quiz started, so they see it.
I hope so.
I can go to the set of 4. Uh, okay, we're back. Melissa, how many answers are we getting there? Okay, we're gonna try. Just crazy. We also had to change the computer that's running uh, everything here last night. So just all kinds of new stuff technologically coming into place. So um, I will attempt to show you Melissa's screen. Fingers crossed. Melissa, do you have the iClicker? Just go to that PowerPoint and the iClicker displayed.
I click the poll and then it disappeared.
Okay, just
I stop the poll and then I click the results.
okay, let's see if it's on the other display here. It shouldn't, because those are just mirrored displays, as far as we know, right? Maybe we should check. It is there. Can you drag it down from there? Okay, sorry for the technical problems here. You are equally distributed among A, B, and C there. That's interesting. Let me give you my thinking on that. So what you're saying here, what we're saying here is pH 8, we understood that it was blue. So if I have 3 colors that it can be, red, yellow, and blue, and it's absorbing in these areas, which absorbance is causing the blue color? C was a little bit more popular. So we harken back though, if something absorbs blue, what color is that thing? That thing isn't blue. If it's absorbing blue, the blue doesn't get to your eyeballs. So I think the C people were thinking, well, blue is the shortest wavelength, the highest energy of the spectrum, so it's absorbing here. So this is a good callback for you to remember that it appears blue, so it's absorbing in the reds and yellows. So the best answer here is it's absorbing in the red, which is the lowest energy of the red, yellow, blue transitions. So it's actually blue absorbance and the yellow absorbance, and the red absorbance is the highest energy because the color is the complementary color. After you absorb, that color is removed from the spectrum. So good, I'm glad we went over that to remind you of absorbance and color. So here's something you'll be very interested in, especially if you're going into biological sciences, maybe even medicine. your blood buffer, we finally got into a situation where we can look at a biological system very carefully. And actually, from here on, we're going to talk about biological chemistry. And I'll say this again, remind me to say it again, but we're going to look at a lot of different biological molecules. You're not responsible for any biological molecular structure. So all we're interested in is the properties of the biological molecules. So we'll focus on parts of the biological molecules that we understand, but their overall structures, you're absolutely not responsible for. As far as we're concerned, they're pictures. We'll treat them as pictures now and on the exam. So here we aren't going to even show you any hemoglobin, any blood proteins. We're just going to think about the blood as a fluid. So, and apply a lot of the things we know. So your lungs, when you breathe in oxygen, you exhale carbon dioxide and water. Breathe in, breathe out carbon dioxide and water. So the act of breathing regulates, if you're breathing normally at a normal pace, the partial pressure of carbon dioxide in your lungs stays at about 40 torr, a fraction of an atmosphere. But we know that partial pressure would correspond to a concentration of dissolved carbon dioxide. And that concentration of the dissolved carbon dioxide would be maintained if you're breathing normally, because the partial pressure would be normal, steady. Carbon dioxide in your blood is converted to carbonic acid. There's an enzyme that does that, carbonic anhydrase. So once the carbon dioxide is in your blood, carbonic anhydrase will convert it to carbonic acid. So you have Henry's law working in your lungs. You have an enzyme, a protein enzyme working in your blood. And that protein enzyme is maintaining the concentration of the HCO3, the base form of this acid, at about 24 millimolar in your blood. So you have the acidic form being regulated more or less by breathing. That's what you can give you a supply of the acid form, and then the carbonic anhydrase action regulates the concentration of HCO3. So you see there's an HCO3, H2CO3, a carbonic weak acid, weak base interaction. Your kidneys are very sensitive to the HCO3. So they can control how much of that base form leaves your body. So all the forms of this carbonic acid are regulated, and when you hold them at fixed concentrations, you fix the pH, because this is a buffer. So we can fix the pH of our blood by using the carbonate buffer. So we've got the carbon dioxide anyway. We buffer our blood with it, controlling by the kidneys and the carbonic anhydrase and the carbon dioxide we're breathing in. And we know the pKa of carbonic acid is 6.1. And this second equilibrium has a pK of 10.2. So we can calculate what is the pH, because we have the concentrations of the weak acid and the weak base. We keep CO2 at about 1.2 millimolar. That carbonic anhydrase keeps those concentrations about the same. So we have 1.2 millimolar of the weak acid. We have 24 millimolar of the weak base being controlled by the kidneys. So we can plug that into our expression. We can say, well, the pH is the pKa, and the one we're interested in here is the first dissociation, because those are the concentrations we're controlling. So we can put the weak base and the weak acid in there. The pKa is 6.1, and these concentrations we can put in there and come up with a pH of 7.4. So that's how your body maintains a pH, a blood pH. You can have hyperalkalosis. You can have too much base in your blood, or hyperacidosis, have too much acidic in your blood. Your pH gets too low. Or you could imagine if you were hyperventilating, breathing in and out too fast because of stress or something that's happened. If you're breathing in and out too fast, that would reduce the partial pressure of carbon dioxide. You'd be exhaling it very rapidly, probably before enough of it's produced in your body. So that pressure would go down, concentration of the acid form. So you lower the concentration of the acid form, and the base form starts to dominate, and the pH of your blood would rise. And of course, that's dangerous. Your pH has to be constant. You've seen, I think, maybe on TV, someone will be hyperventilating, and a EMT or something will have them breathe into a paper bag. Here, breathe into this paper bag. And you can imagine what that does. If you breathe into the paper bag that's collecting the carbon dioxide that you breathe out and making you rebreathe it, artificially increasing the partial pressure of carbon dioxide. Very slow. It might be unusably slow on the live stream this morning. Do we have any feedback from people watching?
It keeps them buffering, very blurry, super blurry, very blurry.
Okay. Last time. Yeah. We will try to switch to Zoom like we did last time. Zoom is a much lower bandwidth requirements, and hopefully we can get that to work. So stand by. I know you're seeing this in delayed action. We'll start a Zoom and try to go through that. So stay in the Zoom. Can people hear me in the Zoom room?
Yes.
That's a yes. Okay, we'll switch to Zoom. Zoom is inherently lower bandwidth, so it'll be blurry no matter what. So if you can tell if it's too blurry, we will try to fix that. What's the Zoom look like on your machine? Are you on?
I asked Ryan to mute everyone.
Actually, everybody's video, yes, of course, and then the live stream, so we don't have that bandwidth going on.